Good afternoon. Good afternoon. We are two MEDICS. MEDICS stands for Medicinal Effects Detected in Chinese Stage. I'm Melissa. Also presenting today is Brian and Nick. Other members of our team are Jack, Hugh, Frank, Cynthia, and Hubert. We would also like to acknowledge our librarians, Huvenka and Jim, and also our mentor, Dr. Goldberg. So the main focus of our research was Chinese sage or Danshen and its major component, salvia acid B. We wanted to focus on Danshen for cancer research and wound healing because it is a traditional medicine. Herbal medicine has been used for thousands of years, and specifically in China since 100 AD. In China today, more than 3,200 herbs are used in over 400 formulas today. And in the United States, Taxol is used to treat breast cancer, and it is derived from the Pacific yew tree. Danshen is commonly used in traditional Eastern medicine to treat cardiovascular diseases and ischemia. Its major component is salvia acid B, which is the major component of Danshen. Danshen's medicinal effects can be contributed to salvia acid B and its structure, such as its aromatic rings, which give it its stability. So as we continue our literary research, we began to focus on salvia and wound healing. Previous studies have shown that salvia reduces the incidence of necrosis and ischemia in post-operative patients. Necrosis is unregulated and undesirable cell death. Brian is going to talk about this a little bit later. Ischemia is a restriction in blood supply, and this is problematic in post-operative patients because blood supply isn't being provided to the area that the operation occurred. Salvia also prevents cardiovascular remodeling and increases in vitro angiogenesis. Angiogenesis is the formation of new blood vessels and with an endothelial cell binding. So this led us to our first aim, which is how does salvia affect angiogenesis and endothelial cell migration during wound healing. To test this aim, we first did a scratch assay. For the scratch assay, we plated endothelial cells that you can see here, they're the black dots. And then we scratched the cells, and that's the white line that you can clearly see in the 0 hour. So we scratched the cells, and then we monitored the cells over a 36-hour period and took pictures at 0, 12, 24, and 36 hours. As you can see, as time went on, the scratch became smaller, which represents endothelial cell migration. These are wound healing results. On the x-axis, you see time post-scratch, and on the y-axis, you see gap distance. With all of the concentrations and the control, you can see that over time, the gap distance decreased. However, we did not see a significant difference between the control and our various concentrations. We contribute this to the fact that our model is very simplistic and wound healing is a very complicated process. At this point, we decided to stop research on this aim and to focus on our second aim. Our second aim is to focus on salvia as a cancer treatment. Salvia has been shown to downregulate cell death in endothelial cells and upregulate cell death in cancer cells. This is very interesting for cancer research because the salvia is selectively killing cancer cells. For example, in chemotherapy, all cells are targeted, all fastly replicating cells are targeted, and this can lead to undesirable side effects such as hair loss, nausea, and fatigue. So salvia has been shown to decrease cancer cell viability in head and neck squamous, liver, and leukemia cancer cell lines. Salvia is attacking these cell lines through activation of caspase proteins. Caspase proteins are linked to extrinsic and intrinsic apoptosis, which is another form of cell death that Brian is going to talk about later. So we have chosen to focus on cervical cancer. So why cervical cancer? Cervical cancer is a major health issue for women. In 2010, approximately 12,000 women were diagnosed with cervical cancer, and of those 12,000, 4,000, or 33%, died. Cervical cancer is a larger impact on minority groups such as African Americans, Hispanics, and Native Americans. So the big thing with cervical cancer is there's a lot of talk about prevention because cervical cancer is closely linked to several strains of human papillomavirus or HPV. So currently, there's screening for HPV through a pap smear at the gynecologist. So women will go and get a pap smear every 1 to 2 years, and then if the pap smear comes back with abnormal cell growth, you conclude that they have HPV. There is also a Gardasil shot, which is a vaccine for 4 strands of HPV, and 2 of these strands are closely linked to cervical cancer. However, there are more strands than 4 of HPV, So the vaccine does not account for all of these, and it does not account for all the ones that are going to cause cervical cancer. So at this point, we want to focus more on the treatment of what happens when you do get cervical cancer and not just how to prevent it. And this leads us into our second aim, which is how does SALB affect cervical cancer cell viability. And I'm going to hand it off to Nick, who's going to talk about our methodology and results.
Melissa. So as we set out to figure out whether or not salmonella acid would have an effect in our cancer cell line, in our HeLa-cell model, we first asked ourselves, how really do we measure cell viability? Is it having an effect on our cancer cell line? And the way we do that is through running a clonal assay. So a clonal assay relies on counting the number of viable cell colonies that are formed after a treatment and growth period. And by analyzing or really quantifying these, the number of these colonies, we can determine its effects on cancer cell viability. So we started off, we dilute our cells so that we're plating 50 cells per well in a 24-well plate. What this, in theory, does is they're so diluted that one cell, after we add them to our culture media, will sediment to the bottom of the plate. Then you allow them to be treated for 24 hours, and then you would allow them to grow for 7 days. So this one cell would then divide and replicate and form a colony on the bottom of the plate. If our agent was affecting cancer cell viability, and HeLa cell viability specifically, then we should see a decrease in the number of viable cell colonies at the end of that 7-day period. And on the left here, we have an example of a viable cell colony, which in the literature is any cell colony greater than 50 cells. So in this case, there will be no effect on the cancer cell viability. That one cell is able to sediment to the bottom of the plate and grow out from a viable colony. And on the right, we have an example of a non-viable colony. So this is the data that we collected for our clonal cell assay. On the y-axis, you have normalized HeLa cell viability. So we counted the number of viable colonies, and then we would, through our other, on the x-axis, we have our dosage points at 1, 5, 10, 20, 25, 50, 100, 200 micromolar concentration points. And we would divide out by the number of cells in our control so that we can end up with a normalized percent value. At the 50, 100, and 200 micromolar time points, we saw a significant decrease in cancer cell viability tested for the student t-test. And on the far right, we have store scoring, which is our positive control, a non-selective cell death inducer. So we can see that we have a dose-dependent decrease in cancer cell viability. Okay, so what does this mean? It means that SALB is effective at decreasing cancer cell viability. So a low cancer cell viability means that SALB has potential for research into its mechanism in cancer cells. And the colony formation assay is actually quite common as one of the kind of gold standards in vitro cancer research. All right, so now that we knew that it was selecting against or decreasing cancer cell viability, we wanted to go about confirming that it was actually causing death. So the colony assay could just measure that it was inhibiting cancer cell growth. Now we wanted to check to see if it's actually inducing directly death in those cells. And we did that through our cell death enzyme-linked immunosorbent assay, or an ELISA. So it's going to quantify cell death through the quantity of DNA fragments, which are a marker of cell death. Fragmented DNA was then measured through absorbance in relative light units. So a higher relative light unit would indicate more cell death. Let's take a look at what ELISAs are. So we would first, you have a capture antibody on a solid plate. So our marker, in our case, was DNA, fragmented DNA. That capture antibody doesn't move at all, and it binds an antigen in this diagram, essentially what you want to detect. You would then watch with a secondary antibody. That second antibody would come and bind to that antigen of what you're trying to detect again, and that would be linked to an indicator. In our case, it was an enzyme that can change the color of the solution that it was in, and you could detect then how much the DNA, we quantify the amount of fragmented DNA that was found. Okay. So we treated them for 24 hours, 24 hours time treatment, plated them, or lysed the cells. We have to break them open to get to the DNA fragments, plated them into our ELISA plate, washed and put in our secondary antibody, the secondary antibody bound, forming the sandwich you saw in the last diagram, which then could change the color of our culture media. And this is the data we collected for that experiment. And we'll see on the y-axis we have normalized absorbance, and on the x-axis we have sal-E concentration. So with the past assay, we determined that what we really wanted to look at was 50, 100, and 200 micromolar time points, and those are the ones that we analyzed here. And we see a dose-dependent increase in cell death as a result of salvinic acid bead treatment, which was significant through student t-tests at the 100 and 200 micromolar dosage points. And on the far right, we have our positive control scoring, which is a non-selective cell death inducer. All right, so what does this mean? So an effective cancer treatment, or something that you'd like to research in cancer cells, should be inducing cell death, not only inhibiting growth. So a high relative light unit in this case indicates that sal-E is indeed directly inducing cell death. All right, and to talk more about how salvinic acid bead is killing cancer cells, we're going to have Brian.
All right, so as we've said, we've shown now that both HeLa cells are inhibited and actually dying due to sal-E. Now the next question that we wanted to ask is how is sal-E actually killing cancer cells? And so for that, we need to give you a little bit of background. So as we mentioned before, there are two major pathways in which cells can die. There's the necrotic pathway and there's the apoptotic pathway. So the necrotic pathway is shown here, and it leads to basically an explosion of intracellular stuff basically everywhere. It's very non-specific, unregulated, extremely messy, and can actually lead to really detrimental results. So when you have uncontrolled necrosis, what ends up happening is it can spread to other tissues, and other tissues will start to die. What can this result in is something you probably have all heard of, gangrene. It's a very common illness that results from necrotic tissue buildup, and it can spread, and it has to be dealt with, otherwise the patient will die. So necrosis is a completely unfavorable method of death. So what we actually want to look at is the other side of that, which is apoptosis. So apoptosis, by all means, is the exact opposite of necrosis. It's completely regulated, it's highly controlled, it's safe, it's effective, and it's a clean way that cells can die and will be good out. So the major difference is that stuff that's inside the cells remain inside the cells. They just become these smaller apoptotic bodies that are easily removed from the area by macrophages in humans. And so this allows a much safer mechanism of cleanup. So this is important to our research because when we are using a drug to induce cellular death, it's important that we're not inducing necrosis in these cells. That would be detrimental to the patient's health. So we have to see apoptosis for this to be an effective cancer drug. So the way we can do that is using a nuclear morphology assay. So what this assay does is it looks for one of the first signs of apoptosis, which is nuclear fragmentation. This is just for the DNA, inside the cell, there's a nucleus which houses the DNA. The nucleus starts to break down and starts to sequester its DNA into smaller circular spheres. And so how we can see this is using the Hirsch stain, which will bind to the DNA in fluorescent blue under our fluorescent microscope. So it's very visual and you can see it. And so what we did is, again, we treated our cells with varying concentrations of sal-E. We waited 24 hours, we then removed the media, and then applied the Hirsch stain to the cells. After that, we then put them under a fluorescent microscope and looked for the nuclear fragmentation we could see. And so this is an example of something that we were looking for. And so you can see here, I'll put the arrows here, these arrows are pointing. You can see these small circular spheres of highly condensed blue. That is indicative of nuclear fragmentation there. When you compare it to, say, a cell like this, the whole cell is kind of blue. This just means the DNA is not condensed in this form. It's not actually fragmented. So these are the type of things that we were looking for in the microscope. And so this is what we saw when we actually looked at it. In the top here, you can see our control. These are untreated cells. They're normal HeLa cells. And you can see there's really no apoptosis occurring with normal cells. Then when you look at our positive control by default, you can see right here, there's clear signs of really highly white, very condensed circular formations, which is the nuclear fragmentation we're looking for. And again, no spores form induces apoptosis in these cells. So we should be seeing it here, which is why we use it as a positive control. Then when we look at our experimental stuff, you can start to see, apoptosis occurring here with this nuclear fragmentation in the 100, and we can really start to see it a lot in the 200, where you can see instances here, even here, and then really there's a lot down here. You can see multiple cells undergoing the apoptosis pathway. And so we can quantify these in a bar graph. And so on the y-axis here, we have percent apoptotic cells. So the way we determine percent apoptotic cells is you count the total number of apoptotic cells and you divide it by the total number of cells that are in your field of view. And so that gets you percent apoptotic cells. Then on the x-axis here, we again have cell B concentrations with the control being untreated and then storage form being positive control. And we were able to see that at 50, 100, and 200 micromolar concentrations, we saw a significant amount of apoptosis when compared to the control results. And so we must ask, well, what does this mean? So this assay was set up in a way that is going to effectively tell us whether we have necrosis in our cells or apoptosis. And the only type of cell death that we saw was apoptosis. This is extremely good. Not only did we see apoptosis, but we saw it in a dose-dependent response. This means that the more cell B we apply to the cells, the more cells that die. So this gives us great enjoyment to see that our drug is actually acting in very favorable anti-cancer ways. And so the next thing that we wanted to ask is, now we know it's causing apoptosis, we want to know how it's causing the apoptosis. And again, there are two pathways that we have to keep in mind. So we have the intrinsic pathway over here, and we have the extrinsic pathway. And their names are suggestive of how they start. So the intrinsic pathway starts because of internal or intracellular stresses. There are signals that come from inside the cell that trigger apoptosis. The only real important thing that you need to know here is caspase 9 is vital and important for the initiation of apoptosis via the intrinsic pathway. So caspase 9, intrinsic pathway, remember these things. Then for the other side of the coin, we have the extrinsic pathway. As the name would suggest, it's activated by an external stimuli that binds to the cell receptor and causes apoptosis. For this one, the important protein is caspase 8. So caspase 8 is again vital for the initiation of apoptosis through the extrinsic pathway. So caspase 8, extrinsic pathway. Remember that. For our positive control, so now what we can do is to really determine which one of these is the major player. We can use an inhibitor to knock out the function of one of those major important proteins that I just said. So we can use a caspase 9 inhibitor to knock out caspase 9 function. We can use a caspase 8 inhibitor to knock out caspase 8 function. And then for us, we can use a pan-caspase, which knocks out all caspases as a positive control. And so how can we use this? Well, we can again use that same nuclear morphology assay that we used previous. This time we can add inhibitors. So what we did is we applied a 200 micromolar concentration of salvi, and only that one because we wanted to use as much apoptosis as possible in these cells. So we only used the highest concentration. But in addition to using the salvi, we also applied an inhibitor, either a caspase 8 inhibitor, a caspase 9 inhibitor, or a pan-caspase inhibitor to the cells. And again, we waited 24 hours, we removed the media, then applied the first chain to the cells, and then we looked at them under a fluorescent microscope to look for apoptosis. And so, this is what we found. So again, at the top, you have control, and you see relatively no apoptosis. Then here, we have just salvi. So it's 200 micromolar and only 200 micromolar. And it's similarly, as we saw in the previous study, again, we're getting high levels of apoptosis because we can again see these nuclear fragmentation. Now, this is where things get different. So, when we have our pan-caspase inhibitor and our caspase 8 inhibitor, with salvi in both those, we saw really no apoptosis or greatly reduced apoptosis. However, when we looked at the caspase 9 inhibitor cells, we were still seeing large amounts of apoptosis. So, we can again quantify this result in terms of percent apoptotic cells, just like before, with the percent apoptotic cells on the y, and then the sample name on the x-axis. And for this one, we determined significance by comparing not to the control, but to the salvi sample here. And what we found is that pan-caspase inhibitor and this caspase 8 inhibitor both had a reduction in apoptosis, whereas the caspase 9 inhibitor did not see any decrease. So, you're probably wondering, what does this mean? Well, it means that the way in which we can determine which mechanism salvi is using, whether the intrinsic or the extrinsic pathway, can be determined using this assay. And what we found is that if the assay, or if the caspase that we inhibited is important to function for the salvi mechanism, then apoptosis should not occur. And so the way we can relate this to our results is that when we use a caspase 8 inhibitor, we lost function. We no longer were able to induce apoptosis. However, when we use a caspase 9 inhibitor, we were still able to get apoptosis. That means that caspase 8 is not important, or caspase 9 is not important to the mechanism by which salvi works. However, caspase 8 is important to the mechanism by which salvi works. Now remember, caspase 9 is important for intrinsic function. Caspase 8 is important for extrinsic function. which means that caspase 8 is the dominant is the most important protein out of the two of those, which means that we can say that it is initiating apoptosis via the extrinsic pathway, not the intrinsic pathway, because caspase 8 was important, not caspase 9. So, we've thrown a lot of things at you, and we kind of want to summarize what we did in the large range of effects in which SALB can be used. So the first thing that we told you was that SALB is an effective form of inhibiting cancer cell growth. This is really important for the start of a good cancer drug. Then we looked at to see if it could not only inhibit cell growth, but if it could actually kill the cells. And we found that yes, you can put a check in that box. It does stimulate cell death. But then we had a question of which form of cell death is it going for? Is it doing necrosis or apoptosis? And we found that it actually stimulates the apoptotic pathway, not the necrotic pathway. Then once we had that under our belt, we decided, well, how is it initiating apoptosis? And we found that it was the extrinsic pathway. Now, all of these things are extremely good news for SALB as a potential anti-cancer drug, because it has all the great effects that we would like to see. It's killing cells and inhibiting the growth, and it's doing so in an apoptotic fashion, not in a necrotic fashion. So it gives us it's great for the overall effect of SALB. However, there's still more that we can do. So, for future projects, we would like to actually do a cytotoxicity assay in vitro. And so what the cytotoxicity assay does is it basically looks to see how selective your drug is at killing things. So does it only kill the cancer cells, or does it also kill the healthy cells? And while research would suggest it tells us that there is protective functions and it should only target cancer cells, an actual really in-depth look at a bunch of different tissue types, say like muscle cells, nerve cells, or at skin cells, and looking and applying the same concentrations that we use in this study to those same types of cells, and again looking for apoptosis, would really help prove that SALB has a very selective effect and only targets the cancer cells, not the healthy cells. That would be very good news. So the other thing that we can really look in vitro is, again, delving deeper into this mechanism. I've made a very simplistic view of the extrinsic pathway. It is very, very complex with a lot of molecules in that cascade that actually lead to apoptosis. It is very important to really fundamentally understand how SALB works, to look for and find that first molecule that initiates the chain of events that leads to apoptosis. Once you have that, then you can really have a complete understanding of how this molecule works, how it targets cells, and how it actively kills cells. Then once you have all that information, you can really look long term and look at in vivo testing. So this would actually be using SALB in terms of actual animal models or even in humans to determine, well, how effective is it when you put it in an animal that is multiple different cell types, all different organisms, and how effective of an anti-cancer drug is it? Does it still have the same potency? Is it reduced potency? And learning how to determine which type of mechanism you need to use to actually get the drug inside. These can all be further developed in the in vivo setting. So, this research was a lot of work, intensive, but we had a lot of help to be able to do it. And so we want to thank all those people that really did help us do it. And so we really want to thank our librarians both for their help in the literature review process, so that we were able to really have a good established background before we started research on it. We also really want to take the time to thank our discussants for coming here today, reading our thesis, and providing feedback. We further would like to thank both the HHMI staff and the Gemstone staff for providing the necessary funding so that we could actually perform this research, because research is not cheap. So that was extremely beneficial for us. And finally, we want to thank our mentor, Dr. Volker Ricken, for his continued support, guidance, and expertise in this field, for without which we definitely couldn't have made this research as great as it was. And so, thank you. Any questions? So the question is talking about how the molecule is hydrophobic, is that right? It's the molecule is actually hydrophilic. It dissolves readily in water. Yeah, it's water soluble because hits all over. So the large amount of hydroxyl groups on this molecule causes people are soluble. So the actual mechanism that is discussed in the papers, which we didn't actually look at because we just didn't have time, was this idea that it may be a competitive inhibitor for molecule MMP9. So MMP9 is an important molecule in allowing cells to actually migrate, and it's particularly important in cancer cells because that's how you get metastasis. So the idea is that it's a competitive inhibitor for the MMP9 receptor, and the current research is looking at how MMP9 is stimulate the extrinsic cellular, the extrinsic apoptotic pathway. So that's the current idea of how it's working.
For extrinsic pathway, there must be considered not all terms of receptors. Does the MMP9 look like that?
Yeah, like Brian said, based on previous research, MMP9 receptor, when it's inhibited, actually causes an extrinsic apoptosis, and this was in prostate cancer cells. So yeah.
So that's a connection. Are
And-
there other extrinsic?
Yeah, but the reason that we're talking about MMP9 receptor specifically is that there was a study that found that sal-phenolic acid B actually binds to these receptors in cardiovascular endothelial cells, and it inhibits the MMP9 receptor. But in those cells, it doesn't cause apoptosis because MMP9 is not essential to regular normal cells, but it is in cancer cells. I was talking about the MMP9 receptor, yes. I believe that the ligand would be just MMP9. I'm not sure.
Well, so the question was, do we look at specific protein expression levels? And do we look at the different levels, proteins like P53 and other proteins that are involved in the apoptotic pathway? We did not look at those specifically. We didn't have the resources nor the time. But so we haven't. The reason why we are kind of looking at MMP9, the reason why it came up is that it has kind of variable expression, and that it did. There was a study on cardiovascular. These cardiovascular cells were did bind and inhibit. So it's possible it could be something else, but that's the research perhaps would suggest. But absolutely, for future directions, if we had more time and if we were all graduating, maybe we'd love to go on and look then upstream from caspase.
Yeah, in your thesis, Dr. Oxford must present this I made in the conclusion saying that someone who didn't see the receptor is not antioxidant. But actually, some of these are antioxidant. So, we make this
So the question is about, again, cell and its effect is that it's an antioxidant. So there's basically antioxidants. The reason they're antioxidants is because they're so stable. And all they do is they're able to collect these free radicals because of all these conjugated base pairs here. However, just because something's an antioxidant doesn't mean it always has antioxidant properties. If you increase the concentration enough, or if they collect enough free radicals, they can still become free radical producer rather than an antioxidant in that case.
But you don't have a other evidence to support.
Well, the reason that we ruled out that South B's apoptotic properties were not due to its antioxidant properties, which I think is what you're talking about, is because previous research has found that antioxidant compounds that cause cell death and cancer often do so through the intrinsic pathway, through modulation of cellular death pathways involving reactive oxygen species. And as we demonstrated in one of our experiments, the intrinsic pathway was not involved. Right?
You studied this compound for cancer prevention or treatment. So how about cancer prevention and antioxidant from cancer?
Yeah, I guess that's true, but like you said before, we're only dealing with treatment in the study, not necessarily prevention. For prevention, I suppose it would be useful as something as an antioxidant.
One of the things that makes Salvi so interesting, it's a shame that we actually found in this presentation is actually the vast kind of array of proteins it's affecting, and one of them being cyclooxygenase, decreasing inflammation, which is then shown perhaps as potential chemopreventative, actually to prevent cancer cell carcinogenesis. There we go. So absolutely that could have those properties. We were looking at cell death induction. We basically just, there's a lot of complex effects, and what we were looking at, less than necessarily a potential true chemotherapy agent, more one that, because it has this kind of paradoxical effect, where and actually in one study it was inducing apoptosis in hepatocellular carcinoma, but then reducing apoptosis and has a protective effect on normal hepatocytes, which was fascinating. So that's one of the reasons we originally looked at it. Is it potent enough perhaps to be a true chemotherapy agent? We don't think so, but it has properties which are really fascinating and have interesting implications as far as perhaps future treatments go, or future derivatives or compounds.
I would like to also add on to what Nick said. There have been many studies about Salvi's effects on multiple proteins, and one of them is VEGF, which is important for angiogenesis. And we actually found that it was very interesting how Salvi increases the level of VEGF for angiogenesis in wound healing pathway, but then somehow kills cancer cells. When we think that, like Melissa said earlier, that angiogenesis is important for cancer growth. So that's actually one of the reasons why we looked at Salvi and looked at the two aims, the wound healing aim and the cancer aim. And reason, so I feel like there are not that many labs studying these compounds right now because one of the reasons might be because they is a traditional medicine or compound of a traditional herb, but hopefully our research and I think also your lab will show the rest of America that this is a good candidate for cancer treatment, and possibly also for wound healing, and I know there are a lot of studies with cardiovascular diseases.
One of your results was trying to determine the difference between necrosis versus apoptosis. I was wondering if you actually could measure some necrosis in your assay where you're treating them for 24 hours before you actually look at the cells. Would necrotic cells just be gone from that assay? Can you say that there is no necrosis? And then you see the presence of apoptosis. Does that amount of
There are assays that measure necrosis, but we picked one that measured necrosis. So like there are other assays similar to the Hirsch stain that stains specifically necrosis cells, and it will be able to look at different colors. But so we decided to only go with the Hirsch stain to save some money.
But then would you see an effect of necrosis, like fewer cells? Did something strike you that you never saw fewer cells when you waited for 24 hours and concentration of cells?
So in this assay, it won't pick up the cells that would die necrotically. However, most of the cells that we did see die was you can pretty much attribute to, it was only 24 hours, so the stark difference you might see, like you said, it's only about 20%. Like there were still a lot of cells in those pictures that we can see here. So there's a lot of cells there still. And so like it didn't kill all of the cells, but all the cells that we did see died due to apoptosis and not necrosis.
So would that be consistent with what you saw in the colonies? Because you could figure you could have that reduction in growth because you have fewer colonies starting, or just slower growth of the colonies as you get the same number of colonies starting, but they don't grow as much because they're going. Some of those cells are going in.
Yeah, that would be consistent. So the cell viability assay can detect kind of non-specific inhibition or killing. So the effect of inducing apoptosis could result in a decrease in the number of viable cell colonies, absolutely. In terms of, we didn't do an assay to directly measure necrosis, and it's not directly quantifiable here, but it's strong evidence that it's inducing apoptosis, and it would be interesting to look at that. How it's causing it further, and also going on to look at cytotoxicity assays, hopefully in the future, as a future direction, and looking at whether it's causing necrosis then, or damage or tissue.
Also, on that point is kind of why we had, if you think about it in terms of the story, when we kept asking questions, we saw a decreased viability, and then we wanted to see if it's like cancer, if it was actually inducing death. That's exactly the reason, is that the viability assay is going to give you an overview of, is there an effect? And once we saw that effect, we wanted to really tweeze out the details of that effect. And so that's why we did the ELISA assay to see if it was even causing death. And we found it was. And again, that assay is again kind of not specific, and it could be necrosis, and it could be apoptosis. So then once we found it was causing death, we wanted a really specific assay, and so we picked a apoptotic assay. So then we tested there. So we were kind of follow a linear pathway of thought, and then being able to funnel and get more details down each one of these things, and that's why we did follow-up assays to kind of prove home the point that yes, this is happening, and here's some follow-up studies to show it occurred.
I actually have a quick question. Is necrosis faster than apoptosis because it is unregulated and very disorganized?
You described it as the cells popping, and I think that would be a fairly quick thing for the cells to pop and then be missing.
So, I want you guys to talk about what's the downside of your assay and I know there are many people but it doesn't mean it's one of them. So you actually have some so the assay you use two assays. One is the assay to see fragment of DNA, and the second is doing it in the so what's the advantage is what's cheaper so what's the disadvantage as well?
So for the nuclear stain assay, that's extremely time intensive. It requires you to actually individually count each cell, so that's a major drawback. But as you said, the advantage is that it's extremely cheap. So another type of assay that can detect apoptosis is the annexin-5 stain. You stain it, and then the apoptotic cells will turn red, and you again can see using the fluorescent microscopy. It's more expensive, and so we had this technique used, and we kind of perfected it, so we continue using that. It was also just something that got available, and so that's kind of the alternative the speed versus price is kind of the trade-off.
How do you distinguish an alcoholic cell and
Oh, and the next and 5, they just turn different colors. One is green, one is red. So I think red is necrosis and green is apoptosis. Not apoptosis. When you use an X and 5, you have to apply like a secondary that reacts with molecules that are indicative of the product. So when the cells explode and all the intercellular stuff comes out, specifically, I know when apoptosis occurs, you get the destabilization of the mitochondrial membrane. That sends a signal to the membrane on the outside, which then is what reacts and makes that green color. Whereas the red color is reacting of a different species. It's supposed to be inside cells.
Well, thank you